Thank you. So my name is Jiwon. I'm a PhD student at Stanford University, and I'll be presenting SociaLite. It's a high-level query language for parallel data analysis. This was a research project at Stanford, and we are collaborating with companies and a few other research labs to make it a usable open source project. So first, motivation of SociaLite. So why did we come up with SociaLite? So that's because the existing big data analysis platforms have these problems. So when I say big data analysis platforms, I mean mostly Hadoop-based frameworks such as Giraffe, Apache Mahout, but also including some other frameworks such as GraphLab. So in most cases, they are too difficult to use, even for very experienced programmers, because they provide very low-level primitives. Also, in many cases, they are inefficient because the frameworks are not designed to fully utilize the network bandwidth. And in many cases, distributed data analysis should be network bandwidth bound. And on top of that, with the existing framework, if you want to do slightly different tasks, you need to learn very different frameworks. For example, if you want to do graph analysis, you need to learn to use framework A. And if you want to do some other data mining, then you need to learn to use framework B, which is very different from framework A. So that's a lot of overhead. And that's why we came up with SociaLite. It's a high-level query language plus a runtime system. And you implement your analysis algorithm in high-level queries. And the queries are compiled to parallel and distributed code. And the compiled code is very efficient. It could be up to 1,000 times faster than equivalent Hadoop program if you run it on infinite band network. Even if you run it on 10 gigabit Ethernet, it can be up to a few hundred times faster than equivalent Hadoop. And even compared to some of hand-optimized C code, it can be sometimes closer to, the performance can be closer to those manually optimized C code. And it's Hadoop compatible, meaning that you can read data from Hadoop distributed file system. And we have Python integration to make it easy to express many of the graph and data analysis algorithms. And with this query language, you can do all of this. You can do all of these tasks, plus these other tasks as well. So you can do data cleaning, exploratory data analysis, and data mining, graph analysis, and some visualization as well. I'll be mostly focusing on this and a little bit of this in demo, but you can do the rest easily with SociaLite. So with that, I'd like to give you outline of the talk. First, I'm going to cover programming concepts in SociaLite, the primitives that you use in SociaLite, so distributed tables and SQL-like rules. And then I'm going to present the actual analysis algorithms implemented in SociaLite. Some of them are graph algorithms, and some of them are more closer to data mining algorithms. And I'm going to give you evaluation numbers, and I'll show you some demo. So distributed in-memory tables are the primary data structure in SociaLite to store user data. And they are column-oriented storage, meaning that items in the same column are contiguously stored in memory. And this statement declares a SociaLite table. So you first write down the name of the table, followed by column declarations. The type of the column can be primitive types, int, long, floatable, or it can be also object types, strings, or any user-defined types. And we make it possible for you to control the structure of the table by having some table options. Like you can add indexing to a certain column, or you can, apply sort by to a certain column, or you can declare that, for example, this table is a multi-set instead of a simple set. So let me give you a specific example. So here we have 4 table declarations in SociaLite. The first 2 ones are when you have single machine, and the second 2 ones are when you have multiple machines. Here we declare the table named foo having 2 int column, and this is an example of this table having 4 tuples. And this is the same, was very similar table with 2 columns, but the second column is nested, which is indicated by which is indicated by this parenthesis. And if you nest the second column, then SociaLite creates this kind of data structure to store the tuples. And notice that this stores the same set of tuples as in here, but it stores in more compactly in this adjacency list style data structure. So this comes in handy when you need to store graphs. The third one here declares a distributed table with this angular bracket here. And when you have this angular bracket, we horizontally partition this table by the value of this partitioning column and store the table across those cluster of machines like this. And we use the value of this column, partitioning column, to decide where these tuples must be located. The last one here have this 0.10 inside angular bracket, which is called a range operator, which indicates that the value of this column is between these ranges. In which case, we apply range-based partitioning, where say you have two machines, then the tuples whose first column value is between 0 and 5 are stored in machine 1. And tuples whose first column value is between 6 and 10 are stored in machine 2. Compared with the previous case where we apply hash-based partitioning. Okay, so we let you control this partitioning a little bit with this simple annotation. So once you store, data in tables like that, you can use this kind of SociaLite, what we call rules, to process the data. So here's the example of SociaLite rule. What is on the left-hand side of colon dash is called rule head, and what is on the right-hand side is rule body. So basically what we are doing here is we are joining the tables in the rule body and storing the join result in the rule head in this full table. So let me give you a specific example. So let's say we have these 5 tuples in bar table and these tuples in cox table before we evaluate this rule, and full table is empty. So as we evaluate this rule, we go over the tuples in bar table one by one, and for each tuple in bar table, we go over the tuples in cox table and trying to find a matching tuple whose first column value matches to the second column value of the tuples in bar table, and that is because we use the same variable name here, b, so we want them to be equivalent. So we have these matching tuples, and we store the kind of join result in the full table, but only A and C, which is this guy and this guy. So we have another matching tuple here. So after we evaluate this rule, we have these 3 tuples in full table. So let's have another look at this example here. So these are distributed tables. So if you have 2 machines, the tables are partitioned into 2 and stored across these machines. For this tuple in bar table, we have matching tuple in machine 2. So for this, you need to transfer this tuple to machine 2, which is automatically handled by a SociaLite runtime system. And we do the join operation on machine 2 and transfer the join result back to, well, wherever it should be stored, in this case, back to machine 1 and store in the right partition. And we, of course, we do not transfer a single tuple at a time. We, create a temporary table and, accumulate some number of tuples in the temporary table and transfer the table in a single message. And we pipeline this communication and computation so that we can fully utilize the entire system resources, CPU and network bandwidth. So if you use InfiniBand, if you use 10 gigabit Ethernet, we fully utilize this entire bandwidth. If you use InfiniBand, which gives you about 5 gigabyte per second bandwidth, we can use about a little less than half of it, up to 2 gigabyte per second. That is better than any of the Hadoop-based distributed data analysis framework. So although we automatically handle this distributed computation, distributed join operation, we let the users, the programmers, to kind of control this communication pattern a little bit by the order of table in the rule body. So if you have bar table first, and then Quarks table, then we transfer the tuple in bar table to where the matching tuple in Quarks table are stored. But if you reverse it and have Quarks table first, then we transfer the tuples in Quarks table to where the matching tuples in bar table are stored. So going back to the previous case, so in this case where we have bar table first, we know the value of B already, so we know where the matching tuples in Quarks table are stored because this determines the location of the tuple in Quarks table. But if you reverse these two and have Quarks table first, then we do not know the value of this A, which is in the partitioning column. So until we actually do the join operation, so we need to broadcast this tuple to the rest of the machine in the cluster. So depending on the relative size of the tables and partitioning scheme, this may or may not be better than the previous case, and we let the users to control this communication by having by this ordering of the table in the rule body. But in the future, it's of course possible for the SociaLite runtime system to automatically optimize this to have minimum communication volume. So we make use of multiple cores on a single machine by having multiple sub-partitions of tables. So if you have multiple machines and the tables are partitioned into two, but for each partition on each machine is further divided into multiple sub-partitions, and for a given evaluation rule like this, we create evaluation tasks, multiple evaluation tasks, as many as the number of sub-partitions in the first table in the rule body. So in this case, for this rule, we create 4 evaluation tasks on each machine like this. So we create up to 8 evaluation tasks, and these tasks are dynamically scheduled and executed in parallel by multiple cores. And we automatically add synchronization code if that is necessary, so users do not need to worry about the synchronization at all. And aggregation is, of course, very important in data analysis, so we support them in SociaLite. You can use aggregate operation by having this aggregate function in the rule head. And the semantic is that, in this case, we first group by the tuples in the full table by the values that are before this aggregate function. So we group by the values of A. And then we apply this min aggregate function to the second column of the tuples that are in the same group. We have built-in aggregate functions for common aggregate operations, min, max, sum, average. But we also let users to implement their own aggregate functions either in Java or Python. And unlike other query languages, SociaLite very well support recursive rules, which is important in graph algorithms such as BFS, which involves recursive traversal from one node to another, to their neighbor node. And here's an example of recursive rules in SociaLite. They are indicated by having the same table name in the rule head and rule body. And semantic is very simple. We repeatedly evaluate this rule until there is no changes to the full table. So we evaluate this rule once and add tuples to the full table in the rule head. And with that added tuple, we evaluate this rule body again. And that is repeated until the table in the rule head, full table, does not change at all. So with this recursive rule, and with aggregate function, you can implement core graph algorithms, such as shortest path algorithm implemented here in SociaLite. Here we have implemented single source shortest path algorithm, where you have single source node, and you compute the shortest distance to that source node from the rest of the node in the graph. So the graph is stored in this edge table: source node, first column, target node, and edge length. And we index it by the first column. And the result of the shortest path computation is stored in this path table. So for each node in the graph, you store the shortest distance in this path table from a designated source node. And here in this 2 lines of code, we have implemented shortest path algorithm. We have two rule bodies, one here and another here. And the semantic is very simple. We apply this mean aggregation to the tuples from both rule bodies. And the first rule body is a base case for the recursion, where you're setting the shortest distance to a source node itself is 0. So we are setting, assuming that this is source node, we are setting the distance to this guy itself is 0. And that is added to this path table, which triggers this recursive, this rule body, so recursive evaluation. And for the neighbor node of that source node, we are updating their distance to be 1 in this case. So in the first rule body, we are setting the distance for this guy. Wow. Okay. And for the second rule body here, we are updating the neighbor node and then recursively to their neighbor node. And because of the characteristics of some of this aggregate function, we can apply prioritized evaluation and incremental evaluation. And if you run it on a single machine, we can kind of compare it to Dijkstra's algorithm, Dijkstra's shortest path algorithm. And if you run it on a parallel multi-core machine or distributed machine, we compare it to something very similar to parallel data stepping algorithm, which is one of the fastest parallel shortest path algorithm. And the details are in these two papers. And we have Python integration. Well, it's mostly Jython, but we let you intermingle Python code and SociaLite queries in the same file, as long as you embed the SociaLite queries inside this backtick. So for this, we extended Python interpreter to pre-process the SociaLite queries. And we support full interoperation between Python and SociaLite. So from SociaLite queries, you can access Python functions and variables. And from Python code, you can access the tuples in SociaLite tables. So let me give you an example here. So here's how you intermingle Python code and SociaLite queries. So this is Python code. And here's SociaLite query declaring a table and inserting a tuple into the table. And here we have Python variable, and you're accessing that Python variable inside this SociaLite rule. And you can also access Python functions from SociaLite rule, but we want you to annotate its return type so that we can optimize it with respect to that type. And finally, you can access the tuples in SociaLite tables like this. So you can go over the tuples and print the content. So wherever if you're connected to a cluster, then the SociaLite queries are processed in the cluster and stored in the cluster memory. And wherever you're running this script, when you're doing this operation here, then we are fetching the tuples from the cluster to wherever you're running this, so that you can easily examine the either analysis result or intermediate result. So let me quickly go over some of the algorithms. Shortest path, which is already covered. And Eulerian path algorithm, it can be also implemented in SociaLite like this. I'm not going to go over the details, but this algorithm is very important in bioinformatics when you for the genome assembly tasks. And this PageRank algorithm can be also implemented in just a few lines of code. Let me go a little bit deeper into this. So let me compare. Well, to easily describe it, let me compare it with the Wikipedia description of the algorithm. So this is Wikipedia description of PageRank algorithm, and here's the initialization, which maps to this guy here. And here's what you compute at each iteration. And this is a constant part, and this is where you actually use the link structure to compute PageRank. And this constant part maps to this guy here, and this part maps to here, where we are going over the PageRank. We are using the PageRank value of node pj to compute pj at iteration t to compute the PageRank value of pi at iteration t plus 1, which is what we are doing here. We are using PageRank value of pj at iteration t to update the PageRank value of pi at iteration t plus 1. And we are summing all the values because we are adding everything here. And this damping factor, and we are using value 0.85 for this. So I don't think I have time to cover other algorithms, but you can easily implement some of data mining algorithms, such as k-means algorithm, in these few lines of query and some Python functions here, or logistic regression as well. Well, here's some numbers. And basically, this shows that for these graph algorithms, shortest path PageRank triangles is as fast as very optimized Java, which is about 30% slower than optimized C++. And it scales very well. With this, you're supposed to read this red line here. So from 1 to 16 core, it scales very well. And compared to, we did some comparison study with Intel Research Lab to compare SociaLite with other frameworks such as Combinatorial, GraphLab, SociaLite, Giraffe. And the performance of SociaLite is very competitive. So the details will be, so I'll have a poster presentation as well tomorrow. So I'll talk about the details tomorrow in my poster session. So let me use some of the Q&A time for this demo. So in this demo, I'm going to use, in this demo, I'm going to use DBLP data, which is computer science bibliography data. And I'm going to create a co-authorship graph from this DBLP data. And the vertices are the authors, which is about 1.2 million nodes. And the edges are, if the two authors wrote one or more papers together, there's an edge. And there's about a little less than 10 million edges. And we are going to examine Dr. Perez's academic network in terms of only computer science research. And we basically run shortest path algorithm from Dr. Perez. And I'm going to use our Gephi interface. So we have a command line interactive shell. But for this demo, I'm going to use this Gephi visualization layer. It's an open source visualization tool. And on the left-hand side, you can enter SociaLite queries. And on the right-hand side, you can see the graph and visualization. So I've already ran a shortest path algorithm, and I'm going to visualize how he is connected to Guido. And this is, let me show the, yeah. Okay, so it's hard to read the labels, but this is how Dr. Perez is connected to Guido van Rossum. So he wrote a paper together with this guy, and who wrote a paper together with this other guy, and ultimately he is connected to Guido here in, I think, 5 or 6 number of hops. And let me do the same for this other. So Rena Barba, who gave a keynote speech today, let's see how Dr. Perez is connected to. Oops, let me clear it and visualize this. So again, in about 5 number of hops, he is connected to, Dr. Perez is connected to Rena Barba. So because we have very easy queryable interface, so it was very easy to integrate SociaLite with Gephi. And you can, again, wherever if you're connected to a cluster, the analysis is executed on the cluster, and you selectively visualize the analysis result in this Gephi visualization. So that was it, and I'm not sure if I have time for questions. Maybe one?
You have 20 seconds.
Okay. So if you're interested, this is a homepage. You can download the source code, binary, everything. And if you have questions, please come to my poster session tomorrow at 2:30, so I can answer your questions. Thank you.